Okay, in this video clip I'm going to take a look at the Bjerksund and Stensland model for valuing American options. This model is a closed form solution. It's an approximation. It's specifically designed to value the American option. The American option presents challenges mainly related to trying to come up with a means by which to deal with the early exercise boundary. And because the American option can be exercised early, that creates the possibility that before expiration the option is exercised. Now, trying to determine the pathway for early exercise leads us very often to a discussion about the early, this is a call option for instance, and the pathway for exercise over the life of the option is defined by the boundary condition. Sometimes that's better viewed and more easily estimated in a lattice type framework, but there is this shape in terms of the boundary. There's a stopping region and a holding region, and it's one of the more difficult areas to deal with in terms of American option valuation. Okay, so I'm going to take a look at the Bjerksund and Stensland methodology. There was a 1993 paper, and this paper is the 2002, and the key things we're going to look at here is setting up the estimation in a C++ compiler and trying to replicate the tables from Table 1 and I think Table 2. What Bjerksund and Stensland attempt to set up here is, instead of creating a boundary, again this is the boundary for the early exercise for the call option, okay, so the solid B optimal exercise boundary, this L star doesn't apply in our case here for the moment, but there is points along which once the stock price exceeds the exercise boundary, then that triggers early exercise in terms of the option. And Bjerksund and Stensland say, look, there's a large part of this estimation that's relatively flat, and probably we can estimate with just a flat boundary. And that was the 1993 paper, which worked with a single boundary, assumption. And the 2002 paper goes one step further and says, look, why not incorporate in two flat boundaries, as opposed to a curved. Now, the big if you like, advantage of doing this is it speeds up our estimation, right? So our estimation, instead of the boundary curving down, right, to the exercise at expiry, we're imposing this double flat boundary, which at best can only be described as an approximation. Okay, now if we go to, but it turns out to be not a bad approximation, right? And how do we judge how well the approximation is arrived at? Well, we can have a look at some actual estimations that are performed. So in this table 1 here, we have values for, in this instance, it's a call option, American call. And we run the American call, American put. For the American call, we have these values of the underlying stock price, 80, 90, 100, 110, 120, those repeat. And then we have varying interest rates, so 8%, 12%, and varying levels of volatility, 20, 40, and then time period from 3 months to 6 months. Okay, and we have a follow-up table, then table 2, and again similar sets of values that are addressed here. And what we have is here we have B equal to 4%. Now B represents R negative Q. If we know what R is and B is equal to 4, that must imply that the dividend, if R negative Q is equal to 4, then Q also must be equal to 4. So R 0.8 Q is equal to 4%. Here R is 12%, B is equal to 0.04. So Q then in that instance must have increased to 8%. So 8% subtracting away from that 12% for R gives a cost of carry of 4%. And then and so on. Okay, so there's just varying permutations here. Okay, so let's start the estimation and see can we replicate some of the values that are in the tables. A couple of things, maybe one more thing to mention here. The large C, large P is coming from a binomial estimation. Okay, so if we can page up a little bit. If we can look at that for a second. So the large C and large P are binomial call and put with 3,201 points, I presume steps, right? And at 3,200 steps, you're hitting relatively reasonable level of accuracy. Typically 15,000 step in Broadie the Temple was what we considered to lead to a true value. So if we look at, this is not unusual that in a lot of the literature, right, when we're comparing approximations, in this instance there was different estimations proposed by Broadie in the Temple, but for a basic tree the binomial was 300, but for true value, okay, for the true value, column is based on binomial method with 15,000 steps, and this was a Cox-Ross-Rubinstein tree for Broadie in the Temple. Okay, so Bjerksund and Stensland, let's run an estimation here then, and we'll create a new project, and I've loaded up Microsoft Visual Studio, and I will create a new project, File, New, and just to note, the files for the C++ solution are going to come from original files developed by Fabrice Roux. So I'm going to put in here, I'm going to go for the general empty project, and I'll just give the name Bjerksund, B-J-E-R-K-S-U-N-D, Stensland, and I'm going to note that the original files here are from Fabrice Roux. Okay, so from Fabrice Roux. Okay, and say OK. Okay, and the project has been created. So we add source files, and these are coming from Fabrice Roux. So existing item, and I'm taking these from my documents folder, and I need to input in source files. So anywhere we see source file, we'll highlight. I'm holding down the control button and then clicking on my mouse as I observe source files. So let's just make sure all the source files have gone in. Okay, they seem to be there. And likewise then I'll right click, add existing item, and this time we're looking for header files, header, header, header again, header, header. Okay, and add. And I might have a look here to see are there any issues in terms of, is there something appearing or is there any errors? Sometimes this creates an issue. Okay, but I have a double /, so it seems to neutralize that. And seems okay. Okay, and I might take a look at these header files then. And I'm just trying to search out is there any potential issues in terms of the syntax that might lead us to have issues in terms of debugging? So let's debug and run, and hopefully it works. Okay, and something seems to be happening, and we have, what do we have? I think we have table 1. Okay, so from recreated, so basically in our debug window here, we have table 1. Let's just compare the values for a moment against the original Bjerksund Stensland paper. And okay, go to table 1. And I'll just minimize that. In fact, I'll pause for a second. Okay, so I've got both table 1 generated by Fabrice Roua's code here, and the, if you like, this C hat and then C double hat. The C double hat is the double flat boundary, and then the C hat, single hat, is the 1993 paper results, and this is the 2002 paper results. So for, if we make the comparison, the tree here, in this instance it's actually a trinomial as opposed to binomial, and the reason why we're using a trinomial, it also gives relatively accurate results. It's perhaps what we might consider as being true or close to true. But the comparisons we want to make are here with the 292 and this value here, so they look the same. 58, 57.7 the same. 35112 the same. 1034, 32 looks the same, and the 20 in the 20 the same. Okay, so that's good. Let's go to the next one. 028 same. 57 same. 348, 349 same. 1031 same, and 20 same. Okay, so still good. 1.05, 1.05, 326, 326, 739, 739, 1350, yeah, same. 2125. Okay, so 2126, same when we do the rounding. 2128. Okay, same. 135, same. 468, 69, same. 1096, 1097, same. And 20 and 20, same. So basically the code here looks as if it's estimating reasonably well. What about over here? 2041, 2041. Okay, and you can make the rest of the comparisons. I'll just go down manually while I pause to check are they the same, but that's something you could do also. Okay, so I've checked here the rest of the results. So this, comparing this column to this, taking into account the rounding, and both sets of values seem to be the same. Sometimes in these estimations, I found when I've used Fabrice's estimations, and go to the solutions editor for a second. When we come into Black-Scholes model here, okay, so actually I had made the change, not realizing, right? This is the code that's sometimes provided by Fabrice. It's Voici-Rosa normal distribution. That code works reasonably well. However, it's an approximation. It's not a close approximation. For better estimation of the normal cumulative probability, you might take a look at the Stack Overflow. I got this better approximation to the normal distribution, and this is coming from Graham West. But just follow the link, you'll see the explanation.